Good morning, class. Today we'll be talking about electron structures, ions, and bonds. I'm Bree.
I'm Caitlin.
And I'm Nancy.
So today we'll be focusing on chapter 15, more specifically chapters 15.1 through 15.4. I'll be doing the ionic bonds and metallic bonds.
I'll be focusing on the electron dot structure as well as the shell model.
And I will be focusing on ionic formations.
So like I said, I'll be talking about the electron dot structure, and that's just simply a notation for that shows the electrons surrounding the atomic symbol. So for example, here for nitrogen, and surrounding it are the dots that are the valence electrons, which can also be found on the outermost shell when looking at a shell model, which we'll go over further in the presentation. Because nitrogen is in group 5 on the periodic table, it also has 5 valence electrons. So that's a simple way when looking at the periodic table how you can tell how many valence electrons the atom or atomic symbol will have. So now we'll talk about the steps into making an electron dot structure. So simply first we'll write the atomic symbol name and then figure out how many valence electrons it has. Like I said, you can do that by looking at the periodic table and seeing what group that atom or that atom falls in. And next we would start at the top of the atom, placing one dot, and then moving clockwise, adding one dot as needed to each side of the atomic symbol. And finally, once all the sides are filled with one dot, if it requires another dot, continue with step 1 and add more. Note that each atomic symbol name, when placing dots around them, are only able to hold 8. There are only 8 groups on the periodic table. So when you have your atomic symbol, you cannot put more than 8 dots around that. So now I will show you an example of me doing this on the whiteboard.
Go.
Okay. So following the steps that I previously talked about for drawing an electron dot structure, I will show you how that's done here. We are going to use the atom chlorine. Chlorine has 7 valence electrons. So we will start by drawing the atomic symbol for chlorine, which is simply Cl. And as the instructions or steps stated, you'll put your first dot directly at the top of the atomic symbol. From there, you start going around the atomic symbol, placing all 4. Once you have 4 on the surrounding the atomic symbol, you want to start back directly at the top next to the first dot that you placed. And then you're going to continue to go around until there is 7. So as you can see, there are 2, 4, 6, and 7. Another thing you want to keep in mind is that there are always going to be paired and unpaired electrons. So for example, here we have a paired electron, and this little guy over here is unpaired. And this is simply because this unpaired guy is just by himself lonely, and these two are together, so they're a pair. Or I can show you another example of an unpaired, which would be chlorine. If it were to have 4 valence electrons, it would go like this, and all of these would be unpaired. Now I will introduce you to the shell model. Each shell is pretty simple. For example, group 7 fluorine has 7 valence electrons because it is in group 7. So therefore on the outermost shell it has 7. Let's note that each shell has a different amount of electrons that it can hold. For example, like helium has 2, and that shell is maxed out. When we look at beryllium, we see that it has 4 electrons. So you are going to fill up your innermost shell with 2 and place 2 on the second outermost shell. How many electrons can fit on each shell? So in a shell, an atom's valence electrons are on the outermost shell, which is typically the 8th shell. And it is important to note that each shell can hold a certain number of electrons. For example, shell 1 maxes out at 2 electrons, and shell 2 can hold up to 8, as well as shell 3. Now I'm going to show you how atoms bond together. Typically when atoms bond together, they form molecules, and so the molecule we are going to make is water, which is simply H2O, and therefore it has 2 hydrogen atoms and 1 oxygen atom. Oxygen has 8 valence electrons, so I'm going to draw that on the board. So like I said previously, you're going to draw your atomic symbol, which is O for oxygen, and then you'll create your first shell. And your first shell has 2. Once your first shell is complete, which it is, because it already has 2, you're going to add the other 6 to make 8. So we'll put 1 here, 2, 3, 4, 5, and 6. So now our oxygen atom is complete. Now we are just going to add on our 2 hydrogen atoms. So we're going to simply just add them over here in this corner. This X is going to classify as the 1 electron that oxygen has, and same for this one that I draw right here. And obviously you're going to need a circle for that as well, and then you're just going to insert your letter H. That shows that it is a hydrogen atom, and do the same over there. And this is simply how you do water, and it kind of looks like a little Mickey Mouse. So continuing up here at the top, we can see group 1 through, let's say, group 8. And here's carbon. It has 4, because it is in group 4, it has 4 valence electrons. And here's the shell model for carbon. On the outermost shell, it has 4 valence electrons because it is in group 4. And on the inner shell, you can see that there are 2 because the first shell can only hold 2 electrons. And for example, here we have gold as AU, and this whole section of the metals are going to be the same as group 2. So because all of these are in group 2, they will all, in their valence shell, only carry 2 electrons.
Before diving into chapter 15.2, it's important to first cover a few essentials about chapter 12.3, such as the atom, which is the smallest unit of matter available. The atom consists of smaller particles, such as the electrons, which are in the outside part of the atom, neutrons and protons, which reside in the inside part of the atom, and the nucleus, which holds the protons and neutrons. As it was covered before, electrons are on the outer side of the atom, whereas protons are in the inside. But what makes it interesting is that electrons are actually negative particles, whereas protons are positive, which means they cancel each other out. For example, in oxygen, an atom has a total of 8 protons and 8 electrons, and it is thus electrically neutral. Neutrons, on the other hand, are completely neutral, and they also reside within the atom next to the protons. The periodic table is important because it tells you all the information that you need to know, such as the atomic number, which is above the element symbol, the element name, and the atomic mass. The periodic table is also broken down by metals, metalloids, and nonmetals. This is important because it helps you realize what type of ion an atom is. The way that you get this information is by looking at the group and the periods. The periods are horizontal rows, whereas the groups are vertical rows. The groups is what lets you know and whether you want to lose some electrons or gain some electrons. Here's a picture that helps us look at the organization of the periodic table. The periodic table is organized by atomic mass and is arranged from groups with similar properties. For example, we can see the period that is horizontal and the group, which is vertical. The family group helps us determine what type of ionic bond we have, whether you lose an electron or gain an electron. For example, in helium, since this row is gases, they are full and do not require any change in gaining or losing an electron. Whereas for oxygen, you will want to gain some electrons. Here we will look at the formation of ions. Ions are atoms with a net electric charge due to the gain or loss of an electron. When looking at shell models, it helps us decipher the type of ion that will be formed. Here we have sodium. When looking at sodium, you look at the outer valence shell and you realize it has 1 electron. And you have to think, is it easier for sodium to gain 7 electrons or to lose 1 electron? Atoms are lazy and they want to do what's easiest. In this particular example, sodium finds it easier to lose the electron than to gain 7 electrons. When you lose an electron, you get a positive ion. And when you gain an electron, you get a negative ion. I will show you how to do a valence shells for magnesium. So magnesium, Mg, has a total of 12 electrons. You will place Mg in the middle and start by filling out each shell individually. The first shell holds 2. The second shell holds 8. The last shell also holds 8, but given that magnesium only has 12, we only go up to 12. So that's an additional 2. Now you have to look at the electrons in the outer valence shell, which are these 2, and think about whether it's easier for magnesium to lose the 2 electrons or to gain the other 6 electrons in order to fill up the valence shell. In this case, it would be easier to get rid of these 2, and magnesium would then become a positive ion, Mg+. In this periodic table, we're able to realize that ions that are formed more easily. Positive because they require the loss of electrons. Whereas in these, they're usually negative because they require the gain of electrons. By looking at the group families, you're able to know whether an ion is positive or negative.
So now that we've gone over ions and how they're formed, let's talk about how they can bond to each other. So what is an ionic bond? As we know an ion is an atom with a net electric charge due to a gain or loss of electrons. So now that we have a positive or a negative element, they can be attracted to each other. So an ionic bond, by definition, is the electrical force of attraction between oppositely charged ions. So here we see a sodium atom has 1 valence electron right here. And this ion is given to chlorine to make this a happy 8 and this a happy 8. This is now positively charged, and this is negatively charged. So these 2 ions would now be attracted to each other. So how is the ionic compound formed? Well, the key points are they must be formed by, obviously, ions. So you need a positive and you need a negative charge. They must be positive and negative. You can't have 2 positives coming together. So the negative and positive attract to each other. And also another key point for this is they have to be a metal and a non-metal. Because if they're both metals, that's a different kind of bond. So here we have, again, the sodium and the chlorine. The sodium is our metal and the chlorine is our non-metal. We now have them in ionic form. So this is a positive charged and this is negatively charged. So now that they're completely separated, they can now come together to form an entirely new material. In this little compound we see, it becomes NaCl, which is sodium chloride. These elements keep their element lettering, but become an entirely new substance. So let's try it with a slightly more complex element. Here we have aluminum and oxygen. So we see aluminum has 3 extra available valence electrons to get rid of. So we have 2 of these, so their charge comes to extra 3 and extra 3, as we see here. So positive 3 and positive 3. And these oxygen need to gain 2 more each for them to be happy. So they'll get 2 from here, 2 from here, 1 from here, and 1 from there. So they'll become positive 3, and then 3 oxygens with negative 2s. So now that we have this new, these ions, how will they come together? What is the new chemical formula for this substance? So we see that we have 2 aluminums, and we have 3 oxygens. So all these elements will be coming together to form one new substance. This substance will be called aluminum oxide, and we bring the 2 aluminum for Al2 and the 3 oxygens for O3, and their charges of +3 and +3, -2, -2, -2. I will show you will lead to the whiteboard. So let's try this out on the board with some math. Aluminum had a +3 charge, and oxygen had a -2 charge. And there were 2 aluminums and 3 oxygens. So let's do the aluminum first. So +3 plus 3 is 6. -2, -2, -2, add those all together is -6. So when you put these two together, their current charge is neutral. Now that we know how ionic bonds form, let's talk about metallic bonds. So what is a metallic bond? A metallic bond is a chemical bond in which a positively charged metal ions are held together with a fluid of loosely held electrons. So here we have the positively charged metal elements. Notice their valence shells are empty because they're all kind of sharing and giving up and taking these sea of electrons, which holds them together. So how do these form? Some key notes to think is the loosely held electrons. It forms what they usually call a sea of valence electrons because none of these truly hold on to the electron. They're all giving it away, taking it, and obviously becoming stable and unstable. And it's always between only metals. There are no other non-metals are in this formula, or it's not a metallic bond. So they share and give up these electrons, and that's how these alloys will form and get their metallic-like look. So now let's test what we've learned. Let's go for a bonding question. What type of chemical bond is NAF and why? So one hint for this is what type of elements are in this compound? Well, first let's look. Here we have metals, which are on the purple, metalloids, which are in the pink, and non-metals, which are in the green. So let's look for the Na. Here we see the Na is in a metals category. So now it can either be a metallic bond or an ionic. Where is the other one? The other one, when we look over, we can see it's a non-metal. So that takes metallic off the table. But let's just confirm more that it's an ionic bond. So let's look at their dot structure. Here we see in the valence electron one extra that it would love to get rid of. And here we see it would like to gain one. So this is highly susceptible to losing this electron. So this could become an ion. And this is highly susceptible to gaining an electron. So this one would also become an ion. So now that they have lost and they've gained their other ones, it's now easier for them to have a positive and negative charge. So it would become an ionic compound drawn together by their charges. This would be sodium fluoride, and it would be the ionic compound.
Today we discussed chapters 15.1 through 15.4. Given today's lessons, students should be able to identify various types of elements, able to point out atomic mass, atomic numbers, and how they convert to ions, as well as creating their own electron dot structures, and able to identify different types of bondings.
So we just want to give a quick thank you to our wonderful school, Cal State San Marcos, our great professor, and our audience, Professor Bruce, as well as all of the helpful websites that we use for our diagrams to present in this presentation. And lastly, we would like to thank the A Scholar Services for allowing us to use their office